Hello students. We've been doing linear algebra, but one thing that sometimes shows up even on the very first day of an undergraduate linear algebra class is matrices, which we have not done yet at all. So that's what we're going to look at now. We're going to try to introduce matrices. So we're going to associate them to linear transformations, but not just a linear transformation, we're going to associate it to a linear transformation from V to W along with a particular basis of V and a particular basis of W. So your linear transformation will be associated to, your matrix is going to be associated to the linear transformation with respect to a particular basis for V and a particular basis for W. If any of those things change, the matrix will likely change. Okay, so let's talk about a little bit of what we've done. Now, what I've done is I've written out all this double coefficient stuff so I don't have to. It's really boring when you're watching someone write out these. Single coefficients, okay, but we have this double index here. So I wrote that out. But what am I saying here? Okay, well, let's go through this sheet. Suppose we have a transformation from V to W. V is finite dimensional. W is also finite dimensional. Since V is finite dimensional, if, say, V has dimension n, we pick this basis, B1 through Bn, n-dimensional vector space. That tells me any vector in V can be written in this form. Now, we know from our results on linear transformations that our transformation is determined by these things, T of B1 through T of Bn. We place our basis vectors inside the transformation one at a time, and it determines the transformation. Why? Well, because T of V is T of this thing, and we can just split up the sums and pull out the scalars to get this. So as long as I know what these things are, T of B1 through T of Bn, I can figure out what anything is. Okay. Now suppose we have a basis for W, C1 through Cm, because W is not necessarily the same dimension. So let's say W is an m-dimensional vector space. Okay there. So then what can we do? Well, we can express each of these TB's, or T of Bi's, in terms of our basis. So we get this. We get these. It's a natural thing to do. We expressed V in terms of our basis right here. So why not express these things in terms of our basis here? And then let's look at what happens to T of V. So we now put our vector V, which is this, inside our transformation. We get this. And then all I'm doing is plugging, nothing fancy here. I know what T of B1 is. It's this. I put that here and this and so on. So I get this for T of V. But notice that I have all of these C1s here and all of these CMs here. So let's try to regroup so that, I don't have C1 appear all these different times. So I only have C1 appear once. So if I try to regroup, what's the coefficient of C1? Well, alpha 1, A11, plus I'm going to get an alpha 2, A12, and so on and so forth. So I get this times C1, and this times C2, and this times Cn. Okay? So what have we done? We chose a basis for V and a basis for W. We know that the transformation is determined by these things, T of Bi. And then I just plugged in T of V after expressing what each of those TBI's are in terms of our basis for W. So I get this. And now the idea is, let's put this in a box. So we put this in a box. And we define this to be the matrix of the linear transformation. So the matrix of a linear transformation T from V to W is defined to be this. Yes, it depends on the transformation. That's how we got the numbers. It depends on the basis for V. That's also how we got these numbers. And it depends on the basis for W. It depends on all of these things. That's how I got these coefficients. Okay, so that's where these coefficients come from. I change anything and it changes those, well, likely changes those coefficients. Okay, Now, you probably have had a certain amount of experience with matrices, and the first thing that you're thinking of is maybe multiplying two matrices, or maybe multiplying a matrix times a vector, or maybe trying to solve a system of linear equations. Well, this is a tool that does allow us to do a lot of different things, and we're going to see that. But the very first thing I want to do is I want to sort of define some operations on the set of all possible matrices. So, right now what we have is we have a matrix which is defined in terms of a linear transformation. So if I want to add two matrices, I want to make sure that makes sense in some fashion. I want to make sure we define that addition that has something to do with our addition for linear transformations. Because remember, we have a way of adding linear transformations and a way of scalar multiplying linear transformations. So those are the things that I want to introduce next. So operations on matrices, that makes sense. Let's do that in the next video.